Hi, welcome back. So we're in Chapter 6, Prediction by RCC, at the outline of Prediction by Regression to discuss the sub-outline of simple linear regression. A table, I could say, well, this is the line. I could have, this is one line, this is the second line, the third line, number of lines. Which one of these lines is the best? So we need a mechanism or establishment to understand how to answer this question. Well, basically, if I draw this, the first line, let's say, with assuming alpha 0 and alpha 1. What this line is telling me? Well, it tells me, give me any value of x. I just go to the line and I will tell you what is the value of the line. There is a distance from the line. What can we call this distance? It's obvious an error. Now, this error only for one point, but imagine if I would have done this for every point. If I take every yi and I just subtract that from the y hat, just to square that term, I take the sum of all the points. Well, what is this? This is called the residual error, where the I here, it's going to be from 1 all the way to n number of points. And if I do this for the second line, and I keep doing as many errors as possible, it would look like exactly this. For example, alpha 1 was here, and I captured the error. It happens to be here. If I take another alpha, get another error here, and if I keep doing that, I will reach to some point here. The minimum error that I can get from all these lines I'm testing, right? This alpha is going to be the best alpha that I construct for this data set. Now, this is the concept that I hope it's quite clear to you. So my point is to keep constructing as many tangent lines on each point here until I reach to this particular point that I am after. The slope of this line is going to be equal to 0. So the task now, we need to take the derivative of this to make the best line among this, to choose. This is the actual approach to do that. Actual equation, it looks like this. Well, you take this sum of every yi minus, so I'm going to substitute actually, instead of keep writing y hat, to take the derivative of this term. First of all, let's take it in terms of alpha 0, and also we need to take again the derivative of this SSR again in terms of alpha 1. In terms of the alpha 0, that's going to be equal to, how about we take the derivative in terms of the alpha 1? Now we have two equations to solve them in terms of one another. So we have left this. I could take this into the form of AX equal B problem. So this is the matrix multiplication problem, which we have seen before. If you reach out to manipulate that to the final equation, so basically when we've done that, we have actually chosen the alpha 0 and the alpha 1, which we believe is going to be perfectly the best line among all these other lines I can possibly do. But my question is, how good is this model? Because I could actually construct every time using this method just a linear model for every problem. But don't forget, in some cases, we might get a data set looks like that. I can choose this line again, and then I capture the errors, and it turns out this line is the best with the minimum error you can get. But actually, it's obviously this kind of data set, it should look like this, a curve instead of a line. How good my model is actually fitting the data. The average value of y, the real y's that I know, in other words, the y bar, expected value of y, if it's normal and everything is okay, it should be somewhere around here. I'm going to construct a new term. I will call it the SST. Just take every value of this y, subtract that from its expected value, and just square it. It's a quantity. This is the beauty of mathematics. We're trying to quantify things. By the way, we're going to take the sum of that, all the point, right? The SSR, we saw it by taking, well, every y of I and subtracted from the y hat, the model that. The SSR is measuring this yi, this point, and this is what I predict. The y hat. To capture the distance here, SSR is telling me what is this. The SST is something else. The expected value of y is this, right? But the yi is this, and this distance here it's going to be the SST. Now, do you see we left this point here? I mean, this distance. What is this distance? This is my y hat, the one I am predicting from the line. How far it is from the actual expected value? This point here is going to represent the SSE. We got these three quantities. Well, obviously, in the perfect world of linearity, you can expect the SST is equal to SSR plus the SSE because all the point will be so close. I mean, you won't get some other point away from there. But anyway, what we were trying to capture is how good my model is fit. It turns out, if you think about it from logical perspective, it means I'm taking the ratio of this line over the entire line. So if you take this SSR and divide it by this SST, which is actually from the point to the expected value, you will get the ratio. And then you take 1 minus this ratio. It will tell you how good your model fit the data, taking into consideration the variation of the data. This is called the R-square measures. Now it is the time to actually take this into a practical example. I'm going to say something before that. Don't forget our major task. We want to find the best alpha 0 and alpha 1. So I'm going to use two different techniques. The first one is using the derivative, as we said here, of this SSR. And also I'm going to use the technique of solving AX equal to B. The question is how to solve this problem, and this is not a square matrix. So we can use another approach. If I take the A transpose A times X and A transpose B, this product is going to be a scalar. The alpha 1 is what we want anyway. And this is again is going to be another scalar S. So alpha 1 is going to be nothing but S2 divided by S1. So I'm going to also use this algebraic technique, but I'm going to actually construct a line space, complete random, of alpha 1, and then I'm going to graph them against the SSR, the residuals, and then I will get like a kind of a parabola, and I want to compare this to the derivative and to this, next using Python. Now basically the exact problem, as we have seen, these 5 points of X and Y using the minimization of the residual error to capture actually alpha 1 and alpha 0. This particular equation to capture the alpha 1 is exactly what I have done here. Alpha 0, if you remember, Y bar minus the alpha 1 by the X bar. You will get the values of alpha 0 and alpha 1. If I want to graph this line, which is going to be alpha 0 plus alpha 1 multiplied by every value in the line space. Let's solve alpha 0 and alpha 1 using the matrix actually multiplication. And just by dividing S2 by S1, you will get the alpha 1. And from there, you can capture the alpha 0, of course, by taking the mean of Y minus mean of X multiplied by the alpha 1. Two different values of alpha, one using the linear algebra, one using the minimization of the SSR. Which one is the best? First, let's actually fit both lines and see what's going on. Well, both of them, to me, seems to be, well, close to the point. A visual is hard to tell. I want to capture is the error. And it's obvious to see here that using minimization SSR was a better than using the linear algebra. So what I have done, I created many alphas here in this interval between 0.20 until 0.98, 500 different alphas. We wish to get to this alpha with the minimum error. So here I'm going to take the derivative only in terms of alpha 1. Then I will get the slope. Actually, this value is going to be the slope of the line. Now, if you look at this tangent line, the slope is not 0. Take tangent of this line. I'm talking about this. Here is the slope. Well, it's getting smaller. How about the next? So it's almost 0. Let's go to this point here. So we are getting away again. Turns out that this point, it's really have a slope almost equal to 0. Last but not least, we need to see how good is this model. But is it really, this data seems to be linear? Well, I think something looks like this, assuming that it's not linear. But still, it's okay, linearity. It's fine to work out in this problem. Now, my R squared is 48, which explains 48% of the variation from the expected value of the data. Now let's use some statistics. This is manually to calculate the correlation, just to show you both of them is the same. This is the library and this is manual. If you square this correlation between X and Y, you will get actually the exact same R square value that we captured. Now we're going to move on to multiple linear, maybe more than 3-dimensional. That's exactly what we're going to do next. I will see you then.